Preparing for live stream.
I have not pressed the button, but actually, yes, I start recording. You're good to go.
Okay. So, I'm here. Yeah, perfect. Go, go, go.
Thank you. So as Daniel said, I will start exactly where we finished the last time. So remember, last time we finished exactly by constructing the free part of the string field theory action, that is the kinetic term, right? I gave you this nice general algebraic form, and then I also went through a couple of examples. So for an open string propagating on a 25 brane in flat space. So the point of today's lecture will be mainly to see how this kinetic term, how this free action gets extended to also include all the possible interactions, right? Because without interactions, we are basically not able to do anything else just than to encode the spectrum of the string propagating on a given background. But if you want to compute anything more complicated, like amplitudes or some non-perturbative effects, we certainly need to know about the string interactions.
Is there any mapping between interactions and the background?
Well, yeah. So in order to
understandable, easy, I imagine there is, of course. But
right. So in order to be able to write down the action, even at the free level, as we were discussing last time, you need to assume that you know the worksheet background, right? That you know the worksheet CFT, right? And then this what we started calling dynamical string field phi is nothing but a linear combination of states in the Hilbert space of the worksheet CFT, right? In this particular case, it's a particular class of states which arise at a ghost number 1 in the open string case and a ghost number 2 in the closed string case, which in this unified language of using this degree, well, degree 2, right? So that is the dynamical string field, is just a generic element in the string space, right? So then of course we will see that in the language of SFT, different backgrounds can be seen as classical solutions of equations of motion, which are derived from this action. So that will be one of the messages which I'll try to convey also today. But then continuing in the recap, so that just focus on this kinetic term, right? So when we vary, we derive an equation of motion, which is precisely equivalent to the statement that the state is physical. It's BRST closed, right? That it's an element in BRST cohomology, right? And the freedom in shifting the state by BRST exact state, right, was precisely reflected by the fact that this kinetic term enjoys a gauge symmetry under gauge transformation, which is precisely a shift of the string field by something Q exact, where lambda was yet another string field, this time arising at degree +1, which plays the role of the gauge parameter.
Can I ask a question?
Yes.
Is there some natural real structure on this Hilbert space?
Which structure?
Real structure.
Real. What do you mean by real structure?
Well, so it's a complex vector space, right? Complex numbers.
Yes.
But then when you write a physical state, like for example the gauge boson,
Yes.
the gauge connection is real.
Yes.
So how do you get? I mean, how do you get that constraint? Why can the connection be complex?
Yeah. Okay. So the important requirement is that after you substitute for the string field, right? So the string field is, generally there are non-compact directions. String field is an integral over momenta, right? And the moment representation with some coefficients, right, which play the role of the Fourier duals of the space-time string fields. So then the important requirement is that the action which you end up with is real, right, as you would have expected in any field theory. So in that sense, there is a real structure. Okay. I think it can be formalized, also in terms of a statement at this level. I just didn't think about it. We can maybe think about it later. Okay. So then, given this intro, we will now we will spend the rest of the lecture trying to build these interaction vertices. In particular, I will try and derive some nice algebraic structure which these vertices have to satisfy in order for this action to be consistent. So now, of course, I have to tell you what I mean by this action being consistent. And this is the basic requirement which goes into the construction of these vertices. And that is that this action needs to be built in such a way so that when we then use the Feynman rules, which are encoded in that action, we need to recover what we call offshore string amplitudes. So now I will spend some time trying to introduce roughly what these offshore string amplitudes are. And for the sake of definiteness and also actual simplicity, I will focus on just the case of the closed strings. So then the result for the open strings I will comment on later in the lecture, and we derived in pretty much a similar way. There is just some additional structure which I didn't want to bother with at this first explanation. So starting with the notion of the offshore string amplitudes. Let me first tell you schematically what they look like. So of course, I mean, they are what you would have expected. There's supposed to be some sort of offshore generalization of onshore string amplitudes. So very, very schematically, in the case of onshore string amplitudes, of course, you remember the task you have to do. You have to take your favorite Riemann surface, which is supposed to represent, the particular element of string perturbation expansion which you want to compute, right? So it usually works at some definite genus and definite number of external punctures. So in this case, since we will not want to be bothered by loop effects, at least at this first level of explanation, I will just consider Riemann surfaces with a genus 0. So this is why I'm putting the 0 here, and punctures which are supposed to represent n external states. So in the case of onshore string amplitudes, I'm supposed to take this Riemann surface, and at each of the punctures, I'm supposed to insert a physical string state, which, as we discussed last time, can be always represented using a state in a worksheet CFT, which has total worksheet dimension 0. So actually, not just the total dimension 0, but since the state needs to be level matched, also the left and right moving conformal dimension 0, right? So now, in that case, it doesn't really matter what kind of local coordinates I choose on the surface, right? Because since the state has dimension 0, 0, right? I can always act on it with any locally with any conformal transformation, and the local relation function needs to stay invariant, right? As long as this is dimension 0, 0 primary, which is always the case for these physical states. Now, if we want to generalize these onshore amplitudes to a generic offshore insertion, where the state is also to have generic dimensions, h and h bar, as long as they're level matched, right? This is now as good as saying that the answer is no longer going to be invariant, under changing local coordinates. So I always have to make a choice of local coordinates around each puncture. So these in this picture are represented by these functions fi of wi, well, where z I don't know to be this kind of coordinate on this Riemann surface sigma 0 n, and wi are the coordinates on these local patches which map a unit disk from this wi complex plane to a disk-like region neighborhood around each puncture of the Riemann surface. So for each puncture where I'm inserting the external state, I have to make a choice of the local coordinates. So that's one ingredient which I need to assume for the computation of these offshore amplitudes. And then the integrand, roughly speaking, of the offshore amplitude would have been given just as a correlation function in the virtual CFT on this Riemann surface sigma 0 n of this schematic form, right? Where I'm inserting each offshore state at the origin of this local coordinate system, and I'm mapping it with this function f of I to the Riemann surface. But now, of course, there is something more to this, right? Even in the case of the onshore amplitudes, what I then have to do, I have to integrate over the moduli space of this Riemann surface, right? So usually this is, I mean, even at genus 0, there is a non-trivial moduli space which is connected with the choice of the positions of the punctures on the Riemann sphere, right? That's that's one thing which I have to do, and then of course I have to choose a suitable measure for this integration, which is also very tightly connected to the fact that in this correlation function I also have to insert some contour integrals of B ghosts, right? So if you remember last time when we talked about the BCFT, we have seen that in order for this correlation function to be non-zero, I need to saturate the ghost number to be +6 in the ghost string case, or +3 in the open string case, right? So the non-trivial correlator holomorphically will C for the C ghost, right? So now, if each of these external punctures is supposed to be represented by the state phi at ghost number 2 in the ghost string case. Now, of course, if there is generic number of punctures equal to n, right? Then I need to compensate. I mean, the ghost number coming from just these phi insertions would be n, right? So in order to get down to 3, I need to compensate by a suitable number of B ghost insertions. So this is the meaning of this. So these are schematically some B ghost contours, right, which will be functionals of the coordinates ui on the moduli space, which very simply you can think of as the position of the external punctures, and these contours are to be inserted inside this correlation function. Right. So then, of course, we in the case of onshore string amplitudes, we are integrating just over the moduli space of the Riemann surface. So now, in the case of the offshore amplitudes, things get a little bit more complicated, right? Because not only we have to compute this correlation function and different points of the moduli of the Riemann surface, we are also making this choice of the local coordinates around each of the punctures at each point of the moduli space. So if you think about this geometrically, that amounts to saying that I have this fiber bundle, right, where the base of the fiber bundle is just the moduli space of punctured Riemann surfaces. And at each point of this base, I'm constructing this fiber, which corresponds to the freedom of choice of these local coordinates. So in total, I'm getting this fiber bundle PG and hat, right? Where this hat is due to the subtlety that which I have not mentioned so far, and that is that each of these local coordinates they can be chosen only up to phase, and this is basically due to the fact that since the states which are to be inserted at each puncture, although being generically offshore, they still need to be level matched. Since they are level matched, they need to be killed by L0 minus L0 bar, the spin in the virtual CFT, and that is they are not going to be sensitive to the redefinition of the local coordinates by a phase, right? So yeah, in principle, I have this freedom of choosing the local coordinates only up to a phase at each puncture. So then, since I'm making a definite choice of the local coordinates at each point of the moduli space, this amounts to making a choice of a section of this fiber bundle, and this section is something which I call this FGN. So this is morally speaking the correct thing to be integrating over in this offshore amplitudes. Okay. So this is a very schematic picture of what an offshore amplitude is. So now let me give you somewhat more formal definition. For instance, I didn't tell you what these B ghost contours as functionals of these coordinates on the moduli space should be. So so they have to be chosen in precisely such a way so that the offshore amplitude satisfies some formal requirements. And these are as follows. First of all, I want to write the offshore amplitude as an integral over this section f0n. And of course, in order for this integral to have an invariant notion, which is independent of the choice of the coordinates on the moduli space, what I need to be integrating over is a P form, right? And the P form and the rank of the P form, P needs to be precisely the same as the dimension of this space of this section f0n. So then, of course, I can talk what are the properties of this form which I'm integrating over. So at the level of this picture, the form will be everything inside this correlation function. So it will be constructed out of these correlation functions on this surface sigma 0n, and also it contains this definition of the measure and the P ghost contours. So then, of course, I need to choose this form in such a way so that this offshore amplitude, when I take these external states back on shell back to be physical, I need to be able to recover the expected answer for the offshore amplitude, right? So then, second, since I can always apply a global conformal map to permute the punctures on the Riemann surface in any way I like. I need to ensure that the total offshore amplitude is totally graded symmetric with respect to the insertions of these states phi1 phi n, right? So that needs to be also reflected at the level of this integrand of this P form. So I need to require that this P form is totally graded symmetric in these phis. And the final property, which needs to be satisfied, is motivated by the fact that when I reduce everything back on shell, I need to ensure that if I happen to insert a state which is zero in the cohomology, but not represented by a zero state, that is represented by something which is BRST exact, that answer is zero. That is, the BRST exact stays decoupled when everything is taken on shell, right? So
the cohomology only makes sense on the weight zero objects, or is there a notion of this cohomology on the whole space of offshore states, or what's it?
Well,
logic or section?
yeah, you will see that at the level of the offshore states where I also add the interactions. The notion of the cohomology needs to be generalized to a more general gauge transformation. So as you will see, the algebraic structure of these vertices which I was talking about will happen to be that of the L infinity algebra, right? And of course, that will also generalize the notion of the gauge transformation. So the gauge symmetry of the full interacting action will no longer be just Q lambda, but it will be corrected by some interactions. Right? So this is the correct generalization of the notion of the RST exactness.
Yeah, I should say I'm a little bit lost in the global logic of what is happening. So is what is happening now? You're explaining how to fix the V ends, or
yes.
are we assuming that we already okay?
Yes. Okay. So okay. Yeah. Okay. Just to repeat what the global logic is, we are attempting to fix the V ends in such a way so that the Feynman rules reproduce the offshore amplitudes, right? So now I'm explaining what an offshore amplitude is, and in a second I will actually take this offshore amplitude and try and reinterpret it as a sum over Feynman diagrams, right? And that reinterpretation will tell me what the vertices have to be.
So to uniquely fix the VNs, it is important to consider off-shell amplitude, because I would somehow think that a string theory is more, at least perturbative string theory is uniquely fixed by the on-shell amplitudes.
Well, perturbative on-shell amplitudes are, yeah, okay, these are unique, but we are not attempting to fix VNs uniquely. There, as you will see, there is a huge non-uniqueness in these VNs, right? Because at the level of an off-shell action, you can always make a filter definition, right? So that filter definition should not affect, you know, any notion of consistency of the action which you're trying to use, right? And indeed, I mean, as we were seeing here, I mean, there was a huge non-uniqueness even at the level of defining what an off-shell amplitude is. Off-shell amplitude is not an observable object, right? Because there is a huge, you know, freedom of choice of this section. I mean, we can choose. I mean, we can choose the local coordinates at the punctures in basically, right? So an off-shell amplitude is not an observable object, and that non-uniqueness in the choice of this section will be one of the factors which goes into, I mean, which is connected to the non-uniqueness of the action, you know, through the freedom of making a filter definition.
Because before this course, my understanding was that
Yes.
there is a perturbative string theory which computes on-shell amplitudes,
Sure.
and then we can upgrade this to a string field theory
Yes.
by taking this input of the on-shell amplitudes, and then we use string field theory to compute the off-shell amplitudes.
No.
What you're saying, we need some extra input to even define what string field theory is.
Exactly. Yes. Yeah. And then yeah, whatever observable we compute with string field theory. Okay, if the observable is to be, you know, associated with an on-shell amplitude, that needs to match with whatever prediction we have from the worksheets, right? So that's the logic. Okay. So in particular, we need to ensure that these off-shell amplitudes are defined in such a way so that when we go on shell, the BRST exact stays decoupled, right? So that is ensured by requiring this strip property, and that can be summarized basically by saying that if we act with Q on the states inside this integrand P form omega, that is as good as acting with an exterior derivative on a form with full rank, right? So in order to see how this works, let me actually show you. So let me assume that I want to compute an on-shell amplitude using this prescription. So I'm integrating over at 0n this form to omega 2 n minus 3. So 2 times n minus 3 is precisely the dimension of the moduli space. Is the real dimension of the moduli space of n punctured Riemann spheres that you can check. If you substitute n equal 4, right? That's the form punctured sphere. You get 2 times 1, which is 2, which is precisely the right answer. 0n. And now let's do what I was suggesting. Let's try and insert a state which is manifestly BRST exact, and let's assume that the rest of the insertions are physical states. So then, of course, since rest of these insertions are physical, right? You can see that the only contribution to the left-hand side of this relation comes from the first term, right? From this Q lambda, right? Then in the other terms, there is Q acting on the other insertions, but these contributions are all 0 because I'm assuming that these states are physical, so they will be killed by Q, right? So so this is directly equal to whatever we have on the right-hand side. So we have an integral of 0n. Sign is not very important because we want to get a 0. So then so we got something which is exact of the integral, so we can use the Stokes theorem to rewrite it as an integral over the boundary of the space M0 is. So now you have to think what the boundary of this space looks like. In particular, what are the Riemann surfaces which populate the boundary of the moduli space? So these are precisely the surfaces which contain at least one degeneration, right? So these are precisely surfaces of the type which we were drawing a lot in the first lecture, where this pinch of the Riemann sphere should be thought of as taking the original Riemann sphere and decomposing into two Riemann spheres which are connected by a very, very long thin closed string tube. So this is a tube-like region connecting the two spheres. Okay. And in a moment we will try and reinterpret it as a very, very long propagator, right, in the language of Feynman diagrams. So now this piece of the worksheet, this tube, can be generated by inserting an operator e to the minus t L0 plus L0 bar, right? So as we will see in a moment, this will indeed turn out to be a contributing piece into the ghost string propagator. And now the boundary is going to be obtained in the limit where t goes to infinity, right? So you can see that inserting such an operator in any correlator in the limit t goes to infinity is as good as projecting any states which are propagating here to lie in the kernel of that guy, right? Because as soon as the eigenvalue of L0 plus L0 bar is non-zero, that operator would project everything else, right? Because it would just go to zero.
Unless there are negative eigenvalues.
Unless there are negative eigenvalues, which can happen in bosonic string theory, but these can be made sense of using canonical continuation. Okay, so yeah, so at the boundary of the space, we are projecting the states propagating in this intermediate channel to be in the kernel of L0. But for generic external momenta K1, K2, Kn, right? You can easily argue that this generically does not happen. This would only happen for very, very special fine-tuned configurations of momenta. So generically, this thing is here. So this is what we wanted to show. So this was just to illustrate how these algebraic requirements give us what we expect for the on-show amplitudes. So now, as I was promising, we want to build the vertices of our SFT in such a way so that the Feynman rules of the action will precisely reproduce these offshore amplitudes, right? So for that, we need to take this result for the offshore amplitude and reinterpret it as a sum over Feynman diagrams. So we are kind of building the action from the bottom up. Okay. So this is our task now. We will try and decompose the space F0n into some subregions. And the first class of subregions are the elementary vertices. So these are the elementary vertex regions. Which I'm going to denote V0n.
F0n is the whole space, the moduli space plus the choice of local coordinates, or this?
F0n is the section. Is the section.
Oh, is this, okay, yeah, it's what you draw.
Yeah, is the section. Here I. So this V0n is a subspace of F0n, such that when I restrict this integral, which comes into the computation of the offshore amplitude just to the space V0n, it will precisely obtain the vertices which go into the action. So this is what we want to show. So this was just to illustrate how these algebraic requirements give us what we expect for the on-show amplitudes. So now, as I was promising, we want to build the vertices of SFT in such a way so that the Feynman rules of the action will precisely reproduce these offshore amplitudes. So for that, we need to take this result for the offshore amplitude and reinterpret it as a sum over Feynman diagrams. So generically, this thing is here. So these VNs are the same VNs as I was writing down just at the start of the lecture. And as I was saying, these are completed by restricting the integral, which is the d0 f. And at the level of the Feynman diagrams, these are to be interpreted as elementary vertices. So now, of course, you can never hope to cover the whole space F0 by just these elementary vertices. So the second kind of region which into which we need to decompose this plane of F0 will be precisely the regions which are covered by the propagators. And these we call the Feynman regions. So these will be covered by elementary vertices V0M, where M is strictly less than N, so vertices of lower order than the number of punctures of the amplitude which we are trying to compute, plus propagators. So in order to be able to think quantitatively, let me first of all talk about the propagators. So the propagators, those can be of course constructed without even having a notion of interactions, right? I mean, using the common law, a propagator should be something which inverts the kinetic operator of the action, right? So in string field theory, even at a free level is a gauge theory. In order to construct a propagator, I first of all need to fix the gauge. And why not fix our favorite Siegel gauge, which we already discussed last time? So we'll be assuming that these off-shell states that are killed by B0 plus, or B0 plus was just B0 plus B0 bar in the Siegel gauge. And in this Siegel gauge, I will show in a moment that a propagator can be represented by this following expression in the Hilbert space, which I will call H. And it's precisely 1 over L0 plus times B0 plus. And this 1 over L0, it is also very convenient to think of it in terms of a Schwinger integral. So that's an integral over T, e to the minus T, L0 plus L0 bar. So this is precisely the exponential which was appearing on the previous board, and B0 plus. Okay. So now let me convince you that that this operator actually precisely does what we need it to do, and that is it inverts the kinetic operator. So the kinetic operator of the SFT is just the BRST operator. So what we need to prove is that when I act with H on Q phi, where phi is generic state, in a Siegel gauge, I will get just phi, right? So let's do that. So first of all, let me notice that since this state phi is in Siegel gauge, I can rewrite this HQ as H anti-commutator Q. So again, this is going to be a graded commutator. In this case, since both H and Q are Grassmann out, right? Because the ghost number of H is -1. This is really an anti-commutator. So why is this true, right? Just think of the other side of the anti-commutator. That would be H hitting directly phi, right? But that is as good as B0 plus hitting the phi. So that is 0 by the Siegel gauge condition. Okay. So then we have to think what this H is, right? So we know that by definition H0 is 1 over L0 plus in B naught plus, right? For L naught plus, we know that it commutes with B naught plus, right? That you can just verify. So this 1 over L naught plus can be taken outside, and we get the commutator or anti-commutator of Q with B naught plus, and that we saw last time that it was equal to L naught plus. So indeed, we get just the identity.
In principle, if we just go back to the origin of reaction and derive the propagators from it, right?
That is what I effectively.
It's equivalent. It's equivalent. It is like a compact way to do it for all fields at once.
Exactly. Yeah. I guess what I'm suggesting, we could just break level by level. Then I have a propagator for the tachyon.
I'm a down-to-earth person. So.
Yeah. So let me actually go precisely in this direction a little bit. Just mention in passing that for backgrounds where there are at least some non-compact directions, where we could have fluid propagating strings along some non-compact flat directions. We were observing last time that the action of L naught plus amounts to acting with k squared plus m squared, right? Where m squared was where m was the mass of the state, right? So that means that for such backgrounds, we can rewrite the propagator as 1 over k squared plus m squared B naught plus. So up to this B naught plus, this is precisely what we would have expected, from a propagator in a field theory. So now, having discussed the propagator, let me come back to our effort of trying to recast the offshore amplitude in terms of Feynman diagrams. So we have seen what the fundamental vertices are. So now we want to cover the rest of the space F0n by diagrams containing at least one propagator. So these are diagrams of that type. So as I was promising, this should be diagrams composed of 2 elementary vertices. Each of the elementary vertices is of the order, it contains a number of external functions which is strictly less than n. So these are some, let's say, vertices. So B0R and B0, and then we need n minus R plus 2 in order to get n external functions in total. So then phi 1, phi now R minus 1, right? Because the R function needs to, R of external state needs to go into the propagator. And then phi R, phi n. So now the task should be to try and represent this diagram, try and implement the Feynman rules using these vertices, right? So at this point, I still don't know what these vertices are, right? But the logic should be that I'm now trying to derive an algebraic relation for vertices, which should be equivalent to the fact that I'm uniquely that I'm completely covering the moduli space of the offshore amplitude by this Feynman diagram expansion.
What about diagrams with more than one propagator?
Oh, yeah, of course, I will need to worry about them as well. For the moment, okay, let me just worry about diagrams with one propagator, and of course there are many more than these, right? I mean, I can also choose to distribute the external states in a different way, and that way I will obtain different channels, right? So there. So now let me just take this particular Feynman diagram. Let me try and write an expression for it. So I have 2 elementary vertices. Let me actually start from the inside. So first of all, I have this vertex on the left-hand side, B0R, phi 1, phi R minus 1. And then the final puncture of the vertex, I need to reserve for the insertion of this end of the propagator. So let me just write down the expression and then I will explain, or just try to explain. So the insertion of the propagator I'm going to implement by the insertion of a complete set of states. And these complete set of states are, the spaces is going to be represented by these states with phi alpha. So then for the other vertex, I need to reconnect it to the first vertex by the basis state phi alpha, phi r, and then phi n. And then just to emphasize that I'm summing over a complete set of state, sum over alpha. So these basis states phi alpha, they are chosen so as to be orthonormal orthonormal with respect to the symplectic form, with respect to this non-degenerate binomial from omega. So this is how this particular diagram would be evaluated using the vertices of the action, right? So then, as Dana was pointing out, in order to reconstruct the complete offshore amplitude, I would not only have to consider different channels of this case with one single propagator, but then also all the other diagrams containing more propagators, which would be corresponding to decomposing these vertices here. Again, these would correspond into resolving these vertices into more complicated subdiagrams, right? But
isn't there some tension between what you're doing and like the usual fact that people usually say in string theory that the amplitude is either a sum of s-channel poles or the t-channel poles, but we shouldn't sum over like plus s plus t?
Yeah, but no, we are not some. Okay. This think of it as decomposing this space f0n into regions which correspond to elementary vertices, which are regions deep inside the middle of the moduli space, right? And then towards the boundaries, you can start clearly saying that some of the diagrams they resemble s-channel, and some of the diagrams correspond to t-channel, right? So the trick is to choose a decomposition of non-overlapping regions of this f0n, where you can reinterpret the Riemann surface as coming close to degeneration.
Can we do some simple? Can we explain what happens for the 4 point?
Yeah. Okay. I will try to explain. I didn't really prepare it, but let me.
This is like all very abstract, and I haven't really I don't understand what is the input and what is the output.
So for the 4 points, right? The moduli space is created by fixing 3 of the punctures and integrating over the position of the 4th puncture, right? So let me represent the moduli space, since you have 2 real dimensions, 1 complex dimension, so the moduli space can be represented by a complex plane, right? Let me denote the position of this 4th puncture as u and u bar. This will be 0, this will be 1, this will be infinity, for instance. So then, in this moduli space, I will have 3 special points, right? I will have point 0, right? Where this puncture approaches the 0 puncture, and then point 1, where this puncture approaches the puncture at 1, right? And then I will have a point at infinity, right? So depending on how I name the channels, I can, for instance, choose that when the moving puncture collides with 0, I will call it an S channel, right? So some finite region, right, around the 0, I will call S channel, right? Then again, there will be a finite region around this puncture 1, which I will call the T channel, right? And then there is going to be some region around the puncture at infinity, which I will call the U channel. E and G. But in general, there is going to be a gap in between those channels, and that is precisely the region which needs to be covered by this elementary.
And the shape of this region is up to the string field theories that's constructing the action, or
exactly. That's yet another freedom which goes into the constructing into constructing the action, right? And again, together with the freedom of choosing this section, that will go precisely into the freedom of making a future definition at elements of T. Okay.
Somehow I was. I understand what I misunderstood. So I was assuming that somehow you were going to say that the contribution of the exchange diagrams to the 4-point functions, the external exchange diagrams would be the same as it would be in quantum field theory, but it's not, right? Because in quantum field theory we would integrate over. Yeah. Okay. No, I think I can't formulate.
But thanks a lot for this question, which and for sending to draw this picture that I think is helpful. So then the basic requirement which should go into construction of these vertices is that this Feynman diagram decomposition, which I was trying to sketch, exactly covers this space F0. So we need to cover F0 exactly once, with no gaps and no overcounting, right? So whatever was missed by these Feynman regions in that particular picture, exactly that I need to cover by the elementary vertex V04 in that case, right? So let's think about what this statement means. So that means that the boundary of the elementary vertex region so del is just the boundary operator here, right? Needs to precisely agree with the boundary of the Feynman region with one propagator in the limits where the Schwinger parameter of these propagators goes to 0, right? So this is precisely the statement about these curves in this picture, right? So perhaps I can make that blue. So this is the statement that the boundary of the elementary vertex region, which is whatever I'm drawing with blue now, needs to precisely agree with the boundary of these three Feynman regions. Okay, so these are precisely the loci in the moduli space where the propagator associated with each of these Feynman regions goes to where the length of the propagator goes to 0, right? So this is of course a correct statement even in the case of the more punctures. In the case of the 4 punctures, of course, I was able to cover the whole moduli space either with elementary vertex or with diagrams with just single propagator. In general, I will also need to consider diagrams with more propagators, right? But you know, those will be then represented by different boundaries. So this is a nice and recursive statement which can be applied to each of these spaces V0 and separately, right?
I think I understand a little bit better what I was confused by.
Yes.
So, well, I guess when you, in the moduli space of Riemann surfaces, when you close Riemann surface, when you have a long tube forming, then this tube is responsible for one complex dimension of the moduli space, right?
Exactly. Yes.
But it looks like in your propagator there is only one real integration. So like you're trading this parameter These one complex, so two real parameters, you're replacing it by one real parameter that you're integrating over this.
Oh, there is one complex parameter which is hidden, which I didn't really talk about, and that is an integral over an angle which enforces the level matching condition, right? So what I'm really inserting inside the amplitude is this times an integral over the theta from 0 to 2 pi e to the minus theta L0 minus. Okay? And that accounts for the other dimension. Okay. Great. So now again thinking about everything carefully, these two statements are exactly equivalent. Covering of the space F0n exactly once with these Feynman diagrams amounts to identifying the boundaries of the elementary vertices with the boundaries of these Feynman regions where these propagators become short. And that is precisely equivalent to what we call the geometric BV master equation. At this point, think about it just as a name. Maybe if I have time, I will try and make a connection to the BV formalism later. So this is saying that the boundary of this space V0n was the following, which I will explain in a second. Going to be equal to 0. So now I need to explain what this operator curly brackets is doing to these spaces or to these subspaces of F0n. So it is doing precisely this, right? So when this long co-string tube, which is representing the propagator, gets to 0 length, what this amounts to? That is amounting to taking the two spheres, which are representing the two elementary vertices going into the diagram, and gluing these two spheres along a disk-like region. So this is the case where the propagator is still finite. Still has a finite length t, right? So now when t goes to 0, this becomes an operation of, I can draw this somehow, of taking the two spheres and gluing them through this disk-like region around this puncture. So that is the same as saying take the two spheres and identify the two local coordinates around the two less respective punctures. So this is precisely what we mean by this. So this then can be the promoted to a well-defined operation on the space of surfaces, which is precisely what we mean by this curly bracket. So this is an operation of sewing. So of taking a surface from each of these two spaces and sewing these two surfaces along these two disk-like regions, right? And that gives us another surface, right? And the space of these surfaces is precisely the space represented by these curly brackets. So that is an operation on spaces of surfaces, which gives us another space of surfaces, which is good, right? Because this is another space of surfaces, right? So and since those are precisely the surfaces which populate this boundary of the Feynman region described here, this statement exactly translates to this statement which I was making before. Up to this sign, so this sign is mostly a convention and is due to the opposite orientation of these boundaries of the respective spaces. So this is how the requirement that we cover the space exactly once, this space F0n, translates to what we call a geometric PV master equation. So let me just make a few remarks. So the main remark is that this actually, if you start this equation, this defines a recursive procedure for constructing these vertex regions. Right? So the recursion at the level starts by making an arbitrary choice of V03. So we pick V03, where it is just a cubic vertex, right? And that amounts to saying that that we just choose suitable local coordinates around each of the punctures of the free punctured sphere, so that the vertex is totally symmetric in the states. But since we know that that this has a zero-dimensional moduli space, I mean, yeah, that should just amount to making a choice. And then the geometric BV master equation tells us that in order to find V04, we have to solve an equation boundary of V04 equals half bracket V03, V03. Then, of course, we can continue cursively. V05 will be defined in terms of V03, V04, etc., etc. So now, of course, in principle, this is an equation to solve. It is a generally a hard equation, and also at this level, it is a very abstract equation. It is just a statement on the spaces of surfaces. So, in order to translate it into something more computable, let us remember this one particular property of the offshore amplitudes. So we were saying that inserting the BIST charge Q inside an offshore amplitude was as good as saying that we act with an exterior derivative on the P form defining the offshore amplitude, and then upon integration over this FGN was translated into acting with the boundary operator. Right? So if we now follow this chain of reasoning backwards, we can take this boundary operator and translate it into an action of Q inside a P form defining the offshore amplitude. And doing that, we can show that the BV master equation, that the geometric BV master equation translates in what we call the main identity for the string field vertices. And that is already a complete algebraic statement at the level of these vertices, E0n. And it can be phrased as follows: V0n acting with Q on all the insertions of V0n, of course, with the appropriate signs, right? So Q is degree odd, so we need to pay attention to the signs when we pass it around individual insertions. So this should be thought of as as corresponding to this term of the geometric BV master equation. So now we have to also represent the operation of sewing the surfaces through punctures, right? And now we have to perhaps I should have also explained the sum over R here. So of course, the particular diagram which I drew on the previous board was just making a special choice of the number of punctures which go to one of these spheres into which I was decomposing the original sphere, right? So, but then of course I have to sum over all possible decompositions R. So this is precisely corresponding to the sum over R here, right? So that was obvious, but I said it nonetheless. So then I have the same sum over this index R. Then I will have a sum which I will explain in a moment. Then I will have a sum over this complete set of states. And this complete set of states is exactly something which I will use again to represent this operation of sewing the two surfaces along these disk-like regions around the punctures. And then also, finally, I need to explain the sum. So I also need to sum over all possible ways of distributing the individual functions, either into the sphere on the left-hand side of the diagram or the sphere on the right-hand side diagram. I basically need to sum over all possible configuration. So this is precisely the sum here. In some schematic, this is like one set I1 I R minus one. And if I take the union of this set with IR dot IN, that needs to correspond to the set one line, right? And I'm summing over all possible, disjoint decomposition of this set into parts. So this is the main identity. So that is sort of the full algebraic statement. So if I test this equation, on some arbitrary states in my string Hilbert space, I'm in principle able to rephrase this as a set of algebraic equations which these vertices need to satisfy. And again, I can formulate the same sort of recursion as I did with the B master equation, and to solve this. So just before we make a short break, let me actually talk about one more piece of this chain of equivalences, which I've been discussing. So yeah, at each point, just it is good to go back and remember the main statement to what let's say this main identity is equivalent to, and that is the requirement that we are covering the space of 0 and exactly once. So we're just now trying to see what this means mathematically. And the final piece, or the final equivalence, which I will give you, is that this main identity is equivalent to the L infinity algebra, what we call the L infinity algebra of string products. So at this point, these vertices, these are just some maps from which take me from n copies of the string Hilbert space to in principle complex numbers, right? So with these string products, the idea is to represent this map V0n phi1 phi n in terms of this non-degenerate bilinear form omega, which was already used to write the kinetic term of the action, and some new maps, which this time take you from n-1 copies of the string Hilbert space and give you another state in the string Hilbert space, which is then overlapped with this final insertion which goes into the computation of the amplitude. And these maps are ln minus 1. So as I said, this should be thought of, ln should be thought of as a map from the n copies of the co-string Hilbert space.
Linear map.
It's a linear map. Okay, so let's talk about its properties. It's a linear map. It's a map which needs to be totally symmetric in its arguments, right? But then, of course, we also know that the amplitude needs to be totally symmetric in all of the arguments, right, including this puncture here. So that map needs to be graded symmetric. and also graded cyclic. With respect to omega. So if you combine these two properties, that Ln is graded symmetric with respect to permutation of the punctures which go inside, and also the graded cyclicity, right, of this map with respect to symplectic from omega, you recover precisely the total graded symmetry of the vertex with respect to all the punctures, right? So then you can finally think about, given these properties, what is the corresponding statement? What is the corresponding algebraic statement at the level of these products Ln, which would be equivalent to the main identity? And the answer is that these are precisely what we call the L infinity relations. And with the plot, there will be a final term where the Q acts on the final puncture. So let me just not write it. And then on the right-hand side, I will have some nested products. Where this sum here is again this complicated sum over these i's, so that we get this joint union of this set 1 plus n. So let me just not write it. Okay. Yeah. So yeah, again, as I was saying, it's good to go back. I mean, what we derive here is that the statement that the L infinity algebra of the string product is precisely equivalent to the requirement that the Feynman diagram decomposition, that the amplitude can be computed by a Feynman diagram decomposition with respect to the Feynman rules, which are derived from the vertices of the SFT action. So let me just write down. Actually, let me stop here and have a short break.
Okay. Yes. Okay, till 11:20. Maybe let's take a break for 12 minutes, or no, it's 24. Yeah, let's reconvene at like 11:25.
It's 1:12 now. I don't know.
Why aren't you summing over different channels? Like for example,
I'm summing over different channels. So the sum over different channels is encoded in this
in the second sum.
in this dot sum.
You had some equation with the curly bees, which didn't have the sum over different channels. That
Yeah, because the channels were already included. I mean, in the spaces, right? You think about. So these spaces were defined already as sum over the channels. Yeah.
So the curly V, so the curly V is some subspace with a moduli space of Riemann surfaces. Is that right?
Yes.
Well, okay, then I guess I don't really understand why you have the choice. Like, can we just forget about this? Can you just forget about this choice of the local coordinates and just talk about the moduli space of Riemann surfaces for now? Is it like, can we frame the discussion in that context? Is there already meaningful in that context?
Yeah, I think so.
Okay, so then consider the moduli space of the four-punctured sphere. It's a two complex dimension moduli space. And then you get some subspace of it by taking two three-punctured spheres and gluing them along some cylinder.
Yes.
Right?
Yes.
So in this way, you're gonna get something, and you're telling me you're not gonna get the whole moduli space of the four-punctured sphere. If I just take two three, right? I take two three-punctured spheres.
Yes.
And I touch some cylinder here.
Yes.
Some nice way, and then I guess I integrate over the t from 0 to infinity, and theta from 0 to 2 pi.
Yes.
Then this doesn't cover the moduli space of the four punctures.
I mean, after you sum over different channels. Oh, even without summing over different channels.
Well, I'm also worried about overcounting, right? If I do this, if I do this in two different ways, it's not obvious at all that there's not going to be some parameter here which maps to some parameter here, so it could even overcount.
Yeah, but even here it is not obvious that you cover the whole moduli space, right? Because for sure, what you're covering here is the region where these parameters go out. I mean, that's sure, and you're covering a finite portion around, around that special degeneration, right? So yeah, then of course, I mean, yeah, if you take this cube to be very, very short, right, then you land at some point, some generic point in the middle of the space, right? But then I don't see how you can get, let's say, the region where these two functions.
That may be true.
So yeah.
Okay, so I can believe maybe that these regions are non-overlapping, that somehow this region is not overlapping with this region.
Yes.
But I'm not so sure about it, because somehow I thought that in string theory was a statement that so this should somehow implement the sum over the S channel poles, and this implements the sum over the T channel poles. But I think the Venetian amplitude is a sum either over the S channel poles or the T channel poles. So I was thinking that maybe actually that this basically a statement that both of these pictures cover the same part of the moduli space. Can you explain what's the logical relationship of that and the statement that the S channel poles? You can either use the S channel poles or the T channel poles.
Yeah, I mean, if you complete the sum over the poles of the amplitude, right? I mean, if you take this cube to be very long, right? I mean, of course, important contributions into the amplitude will come from right? That's right. Yeah, but then if you take into account contributions from open, I mean, if you resum the whole series, I mean, you should be able to get the same answer independently of whether you're expanding around this degeneration or the degeneration. Right. But that is not saying that that is not saying that that the whole amplitude is is obtained as an integral over just the T channel or S channel propagation. These are different statements. I mean, the statement about the poles comes already after integrating over the moduli space. And that is not coming at the intermediate region. That is a statement at the level of amplitude, not at the level of the integrand of the amplitude.
But then where is this choice that we are making? Because in this picture we didn't have to make any choice. If you compute a three-punctured sphere, so pretty much is a unique thing.
Yes.
Then from that you get some very specific fixed region of the moduli space of the four-punctured sphere. You look at what it covers, S plus D plus U. You're left with something, and it's what you're left with is unambiguous to determine. So but you were mentioning that there was some choice of the region. Like you drew this picture with a moduli space of the four-punctured sphere with some arbitrary regions around 0, 1, and infinity.
Oh.
So where does that choice come from?
That was not an arbitrary region, right? So once you make the choice of V, right, then V04 is already determined by this recursion equation, right?
Okay. But I
have to solve it.
The choice of V03 is not I mean, the fact that we have to make a choice.
Yes.
In V03 is not apparent. Just I'm talking about a moduli space of Riemann surfaces because the three branches here is used. is a single point,
Yes.
but there's some extra freedom in this local coordinate.
In this local coordinates, yeah. Yeah.
Good. to book at 6 start.
So we can continue. So now, given this new parameterization of the string vertices, which I've just introduced, that is in terms of the string products L, let me finally write this is an important form of the actions for the closed string field theory. This kinetic term, which we from the last time. It's now the interactions which can be rewritten. Recalling the right symmetry factors which went into the definition of these string products. Suppose so with this wedge n, I'm what I mean is that I'm taking n copies of this phi, and this wedge emphasizes the fact that ln, the products ln are totally graded symmetric in the insertions of this string field phi. So then first we remember that the original pre-action phi q phi was enjoying a symmetry under gauge transformation. So now, of course, if you just try and vary this action with respect to phi and substitute this gauge symmetry q lambda, that interacting action is no longer invariant under that simple gauge transformation. But there is a corresponding generalization. So using the L infinity property, using the L infinity relation satisfied by these products L, you can prove that is a nice exercise that the action is invariant under this interacting gauge transformation. So string field theory, even at the interacting level, continues to be a gauge theory in space-time. So let me now make a couple of remarks and a couple of illustrations. What I have introduced was very abstract. So I think it helps to illustrate especially the logic behind these infinite relations on some simple examples. Before I come to that, let me point out a couple of things. First of all, notice the degree of these products L, right? So we know that the string field phi, which goes into the action, is a state in the string Hilbert space, which is degree 2, in particular degree even, right? Right. So then last time we saw that omega has to have degree minus phi and q has degree plus 1, right? So that means that in order, everything to be homogeneous in the degree, that means that these guys L, I mean, the same as q, they have to have odd degree, okay? So the of L is odd. So that's one thing. Now the other thing, as I was pointing out a couple of times already, There was a huge freedom in making the choice of these vertices and correspondingly in making the choice of these products L. Right. So then you might worry, okay, SFT action, okay, it's a concept which is heavily non-unique, and but this is precisely as it should be, right? Because at the level of the action, we are always free to make a future definition, right? And it can be proved. So for the formal way of proving, see the notes of Ashokson and Martin Zwieback. It can be proved that this freedom in choice of the vertex region is precisely in one-to-one correspondence with the field predicate. All those two fields. So this just adds to the overall consistency of the SFT action. Second thing, you might have noticed that in writing down the original expression for the off-shell string amplitude, I've omitted a factor of G string, right? So we know that in order to be able to recover the correct answer for the on-shell amplitude in particular, each expression for these amplitudes A0n needs to come with a specific power of G string, and that will then proliferate through the computation, and there will be specific powers of G string in front of the interaction vertices in that action. So I was omitting these factors of G string just to reduce clutter. But they will be there, and in particular, those interactions can then be really formally set to zero by setting G string to zero, because these powers of G strings here will be positive, right? So that nicely corresponds with the intuition that as soon as we set G string to zero, we should reduce back to the free theory. Okay, so we have omitted. Now, first, this is, of course, the defining expression for the L-infinity relations, which is at the same time the defining relation for these string products. That is a complicated algebraic relation, right? So in order to illustrate it, let me notice that L-infinity algebra is just a generalization of a simple differential graded Lie algebra.
Just about G string. Can you just shift the G string? I guess I was kind of asking you this last time. Can you shift the G string by changing phi, the part of phi that corresponds to the dilaton?
Yes. Yeah. So that is one thing which you can do in string field theory. You can construct a classical solution, which is going to be a marginal deformation initiated by a special universal state in the Hilbert space, which we call the ghost dilaton. And that renormalizes the value of the G string in front of the vertices. So back to what I was talking about. So in particular, you can make the following choice of these products. So L1 is just a becoming of Q. Okay, I can go at L1 because it is a one product. It is an operator on the Hilbert space taking one state and giving another state. So if we take this L1 to be just a differential on some graded vector space, and if you say L2 to be up to sign plus the Lie bracket. This is a two bracket. It's an operator which it's a product which takes you from two copies of your space to a single copy. And if you set all these L3, L4, etc. to zero, then the first couple of L-infinity relations which you obtain, by fixing the value of n, precisely give you the algebra of the relations of the differential graded Lie algebra. So in particular, if you set n equal 1 in that relation up there, that just amounts to saying that the BRST charge, or in this case, the differential, is nilpotent, right? And if you set n equal to 2, you will obtain a relation which is saying that this differential should act as a derivation on this bracket. And first, if you set n equal to 3 in these infinite relations, you will just obtain the Jacobi identity for these two brackets. Oh, that's nice. But at the same time, this tells you more about what an L-infinite algebra is. So in the cases where this free relation, this free relation would have been completed in the case that L3, the free bracket, would not be equal to 0 by other contributions, right? So these contributions arise precisely in the case where this two bracket L2 fails to satisfy the Jacobi identity. And in particular, if the failure of this Jacobi identity is, so as to speak, up to homotopy, that is, if you can write it as a differential acting on some free bracket, A1, A3, A3, and then of course minus, and then all the terms where the differential acts inside. Again, up to signs. Then this would then this would give you precisely that L-infinite relation in the case of n equal to 3, and so on, right? So because then when this free bracket is no longer is no longer trivial, then there would be a non-trivial relation for n equal 4, which in the case of just the differentiability algebra would be just 0 etc. Okay. So yeah, I hope that illustrates a little bit what an L-infinite algebra is and what it does. So then I had then originally I was going to also make some comments about what happens at a quantum level, because what we done so far was a construction of a three-level classical action. But then in the interest of time, let me completely skip the quantum story, because you will no longer need it in the applications to DC18. So then let me go directly to comment number 5. And that is, of course, so far, what I've given you is just a set of algebraic relation, which these string vertices or the string product need to satisfy in order for the SFT to correctly compute the amplitudes, right? But at the same time, I was trying to sketch a recursive procedure, which in principle would allow you to construct these frequencies. But I didn't give you any particular form or any particular solution to these equations. And indeed, these equations are very, very hard to solve. And they turn out to be actually so hard to solve that in the closed string case, even up to this date, I mean, even up to 40 years after the conception of string theory, we don't really have explicit forms for generic B0n vertex. So in the case of closed string, the concrete forms of examples of string vertices and the generic number of factors are still missing. So what we do have at our disposal are some concrete results only for at lower orders. So we have examples for n equal 3, n equal 4. But then depending on what you want to compute, you can also construct some high point vertices which will work for some special states, for instance, for states which are on shell or close to on shell, but not for generic states. So in particular, as you will see, that is good enough for us to do some order perturbative calculations, but not good enough for us to let's say construct some solutions which we expect to be deeply non-perturbative, like the tachyon vacuum of the ghost string field theory. So that's the situation in the ghost string field theory. On the other hand, in the open string field theory, the
May I ask a
situation.
question first?
Yes.
Sorry, before we depart from closed to open. Can you
Yes.
just summarize like what it would take to get that information?
Yes. So so exactly. I mean, we would need to go and recursively solve this equation, right? So we need to, I mean, each of these vertices V0n, we need to parameterize it with some data, right? So we need to parameterize it with this choice of local coordinates, and then you know, solve for these local coordinates in such a way so as to satisfy this recurrent equation, right? So that in general will boil down to solving some differential equations for these maps at I, which I was showing, right? And yeah, these are hard to solve in general.
But from the point of view of other approaches to string theory, is there some set of computations one could do to then port over to this setting?
Okay,
Like-
I'm not sure I understand.
I'm sure it's I who doesn't understand, but I'm just kind of grasping for why, more about the why there's this void in what is known here from other points of view on string theory.
Well, okay, it would be yeah, okay. I'm not sure what other points of view of string theory would be, at least, you know, roughly equivalent to the point of view which string field theory is trying to take, right? I mean, string field theory is trying to be an off-shell field formulation for strings. So, I mean, if there is something analogous which I can compare to, then perhaps I can answer the question. But
Well, presumably, like string perturbation theory, for the on-shell states, the usual one gives some constraints on these maps.
yeah, but for the on-shell states, I mean, yeah, I don't have to worry about the local coordinates, and which are which is the principal source of all these complications, right? I mean, these are the objects which I have to solve for. Yeah, I mean, going off shell turns out to be difficult. That's what I can say.
Even if you just want to, is there not some like other infinite set of on-shell string perturbative data that could be used to, say, write the n equals 4? If you just fix some low n, you want to
Yeah, so
determine that,
I mean, at each fixed n, you have to solve a finite number of equations, right? Those equations are hard, and I mean, and it goes higher and higher. I mean, you have to solve a higher and higher number of hard equations, right? So that's
yeah. So let's not go higher. Let's just say take n equals 4.
yes.
Like it's not. I'm trying. I guess I'm asking whether it is like understood in principle how one could use data obtained by other means to solve those equations, and if there is no such answer, then it's a little bit one is pretty boxed in. I mean, yeah.
Oh.
Yeah. Like
Okay, I'll try.
the state of the field seems grim if that's the case, right?
Well, there are various strategies to solve for these vertices. There is I mean, there are special classes there are various approaches which may give you some hope. So there is this approach of trying to solve for these vertices. I mean, in the realm of hyperbolic spaces. So that was initiated by Costello and Sweetback. So. Even there, even using this ansatz of hyperbolic vertices at each order, you have to solve some you have to solve some complicated differential equations. So, yeah, there are various approaches. So there is the minimal area approach by Barton's feedback, which is analogous to what is. I mean, that is. Aiming to be a generalization of the written cubic vertex and the open string, which I was just going to talk about. Yeah, but
is there no, just to try to boil this down to something simple, like, is there no even a principle prescription for some more traditional on-shell string computation that if you could do it would allow you to determine the n=4 case?
Yeah, so you're asking if it is, I mean, if just by knowing the on-shell answer, if it is enough to
yeah, so you knew some like huge set of on-shell data, like is it known which data you would need to use to then write this down?
Yeah, that I think is a good question. Okay, I don't have an immediate answer, but I mean, yeah, assuming that you have an infinite knowledge of all possible on-shell amplitudes, I mean, how much you can learn about the off-shell vertex. I don't know, but yeah, perhaps this is something which might turn out to be a good approach.
Okay, so you're saying that not even V4 is known for generality?
It is. It is included in the. Yeah.
V3 and V4 are known completely for all the string theories?
So for the co-string. Yeah. Yeah. I mean this.
Bosonic and superstring?
Yeah, I mean, as soon as you know the answer for bosonic, I mean, the superstring construction. I mean, there is a construction, or there are various construction which just by taking the bosonic input, I mean, they tell you how to distribute the PCOs over the insertions in order to get a correct superstring. Yeah. Okay. So, so in OpenSFT, we can actually do a smiley face because we have a complete action. Because in OpenSFT, we happen to be very, very lucky and show that there is a choice of the cubic vertex, which already covers the complete moduli space. I mean, the cubic vertex plus propagators. With that, we can cover the complete moduli space of any off-shell amplitude at any number of punctures, of open string punctures. And that is the written cubic OSFT.
Is there a simple conceptual reason why it works for the open string and not for closed string?
Yeah.
Prove with pictures or Riemann surfaces and so on.
Yeah. Okay. My intuition for this is that that it fails in the case of the co-string due to the requirement of the level matching. That whatever output these products, I mean, the outputs of these products out, they contain an implicit projector on the B0 minus exact states, right? So even if I try and write down an analog of just taking a homomorphic and anti-homomorphic part of the Witten's vertex for the co-string, right? That is no longer associated as it would have been for the open string because of these projectors in the states. So having mentioned this Witten's open string theory, let me just give you a final remark before I move to giving some examples of classical solutions. And that is precisely how the story will generalize in the case of classical open string field theory. Like by the story, I mean the story which I was telling you so far for the case of pure closed string. So here I'm changing the gears a little bit. I'm instead of discussing offshore amplitudes on Riemann spheres with punctures, I will just sketch what the situation is in the case of offshore amplitudes on disks. With boundary punctures. So again, the integrands, so yeah, this time I'm going to do disks, where the open string states are now inserted on the boundary. And again, I would have been making a choice of the focal coordinates around each of these punctures, right? Where this time I will be mapping this kind of a half disk region to a unit half disk in each of the local coordinates. This is Z disk, and this is WI, and this is I, this is R. Okay. So that would be an analogous picture to what I was drawing in the Gaussian case. So that would be the integrand. And then, of course, I will take this integrand, I will insert some Beagle contours and integrate over the respective section of a fiber bond on modular space. So now, why I'm drawing this picture is, I mean, this is mainly to emphasize one fact. So while I was having a total graded symmetry requirement for the ghost string offshore amplitudes, here, of course, I cannot generate active global conformal transformation to completely permute these boundary insertions. Whatever I do, I need to preserve the cyclic ordering, right? So the vertices of the open string field theory, the interacting vertices which enter the action of the open string field theory will no longer be totally graded symmetric, but they will be just totally graded cyclic. So then the action can be written as follows. In general, where for the open string vertices, I have introduced another set of string products, which take you from the n copies of the open string Hilbert space to and give you another state in the open string Hilbert space. But now there is no requirement on the graded symmetry of these products M. There's the only requirement which I'm the only restriction which I'm putting is that these products M that are graded cyclic with respect to this non-degenerate bilinear form, which give us which gives us these open string vertices. So these open string products M are just graded cyclic. And completely parallel to the ghost string case, the requirement that the Feynman rules constructed from this action give us precisely the open string offshore amplitudes with no gaps and no overcounting of when we integrate over this section of the moduli space. So that requirement is precisely equivalent to what we call the A infinity relations for these products. So again, we would act with Q on all the insertions inside this product N. And then on the right hand side, you get all the possible nestings of higher order products. Minus 82 and minus 1. Some insertions inside, and then also some insertions behind, and then finally we will close with the final. Okay. Well, that is the corresponding algebra of the string products in the open string case. So now, as I was saying, in the open string story, we are lucky enough to have a theory which is just cubic. So that amounts to saying that there is a theory, the Witten's OSFT, in which I can set M3 to equal to 0, M4 to equal to 0 after the graph, right? So if you think about what this amounts to when you expand these infinite relations for n equal 1, 2, and 3, again, that amounts to saying that the BRST charge, the kinetic operator, is not potent as it should be, right? Then the second infinite relation tells you that the two product, this M2, which gives you the cubic vertex, that Q acts as a derivation of this M2. So schematically, that can be written as saying that Q commutes with M2. So this is saying that when I act on the output of M2, that is as good as saying as acting with Q on the inputs. So Q is derivation of M2. And then finally, the analog of the Jacobi identity, which I had for the differential graded D algebra, here is the property that this product M2 is associated, which schematically I write as follows. Right. And again, the favor of associativity would have been parameterized by adding a product M3. But that is not necessary if I choose my open structure theory that to be of this rhythm type.
Can we define string theory to be an A? Can we define open string theory to be an A infinite algebra, or is the inclusion strict? Okay, and a string theory gives you an A infinite algebra.
Any string theory, any open string theory gives you an infinite algebra. Of course, I mean, in order to define, in order to completely specify infinite algebra, I first of all need to specify the Hilbert space on which these products act, right? So
yeah, so you need to specify this omega or something.
Yeah, the Hilbert space, the simple. I mean, yeah, if I want to specify whether the products, whether the infinite algebra is cyclic or not, I need to also specify the omega. But I do about just these relations that I do not know about omega actually, right?
Okay, but is there some kind of like an algebraic definition that's believed to be complete, that once you have a Hilbert space with omega with these m's or l's, then that's a string theory?
Yes. Yeah. I mean, if I give you the open string Hilbert space, so you know on what states these act. I mean, if I give you a background, right, and the string states on the background, and you are able to give me back, a set of products and which satisfy these relations. I mean, that is as good as defining an SFT, right? Because I mean, these steps which I was showing you before, that was a chain of equivalences. So you giving me an infinite algebra is as good as you giving me a suitable decomposition of the section of the moduli space, right?
So the statement is within OSFT, is that like around any background you have this, or what exactly is the statement? That if so you start with some background and you use this within OSFT.
Yeah. So
you go to some other background,
Yeah, so I'm actually coming to this. I wanted to start discussing classical solutions, which is probably what you're referring to, right?
Just to add to Dalimel's question
Yes.
from before, does any A infinity algebra give a consistent string? I guess that was your question. Give a consistent string field theory, or are there kind of interesting constraints coming from the fact that on-shell amplitudes have to be reproduced?
But if your vertices satisfy infinite algebra, then I think it's automatic.
No, we don't know what you. I mean, you want to classify string. I mean, there are different string theories, and they're going to have different amplitudes, and you want to know what is the space of all string theories.
That
So.
makes sense. Okay.
Maybe there are some string theories that haven't been discovered because people haven't classified this algebra.
I mean, yeah. The statement is, I mean, whatever. Okay, it depends on what you call like separate or non-equivalent algebras, right? I would say that if you know, two different sets of infinite algebras are equivalent under field theory definition at the level of the action, I mean, they should in a way be you know, call the same infinite algebra.
Do we have any idea of what, like, is this notion of equivalence sort of well understood, or?
Yeah, I'm not sure I know the answer. I'm not such a big expert in this algebraic formulation of complexity. I can think about it. So
There's some in this discussion of, well, maybe this is best suited for the when we transition to the 2D CFT part next time. But let's see. In this classification question of string theories, is there some purely is there some purely 2D CFT language one could use?
pure 2D CFT. Yeah, I think the answer is unfortunately no. And that's I think it's both a bug and a feature. I mean, it's a bug in the sense that, I mean, it would be very nice to have like pure 2D CFT formulation of what we do. I mean, perhaps this thing which we call the boundary string field theory goes into that direction, or the background independent string field theory, people sometimes call it. So that is a formulation of SFT which is very, very similar to conformal perturbation theory, right? But yeah, that formulation has many problems, I would say. So yeah, so on the other hand, the 2D, I mean, this kind of even at the level of the written source SFT, as you will see next time, it is far from obvious that what we are doing is somewhat equivalent to conformal perturbation theory, right? But then again, you will see that you know, trying to answer questions in conformal perturbation theory using written source SFT, I mean, gives you a completely different language, which in many ways gives you many situations gives you a huge advantage. So we will see that the computation which in conformal perturbation theory, I mean, is done at 3 pages, will be done using written source SFT in 3 lines. Yeah, but the price you have to pay that it obscures the pure 2D CFT data. Perhaps just to you know, make things clear. I mean, in all what we've done here, I mean, we had to specify the consistent string backgrounds we were starting with, right? I mean, choosing different products and is not in any way connected in choosing or classify different string backgrounds. The string background for the given SFT was fixed at the beginning, right? And different choices of ends should correspond to future definitions, not, you know, going to different backgrounds, right? So, what Honest implements, you know, looking for different backgrounds, starting from a given background, are the classical solutions. So in the conventional first quantized, string version perturbation theory, we usually have like no choice but to just refer to background which we specify, right? Given the background, we can compute all the observables on shell data, on shell amplitudes, blah blah blah, right? But then in SFT, and yeah, that's one of the advantages which I was mentioning in the first lecture, we can do more, right? We can take the SFT action as a variation principle. You can derive the corresponding equation of motion. And then the claim is that the field configurations phi star, which are solutions to this equation of motion, of course, after gauge transformations, should be interpreted as giving you different and in general non-perturbative backgrounds for a classical string. So you can do this exercise. For the sake of definiteness, I've chosen this L-infinitive form of the action, that is the closed string. And upon varying this action, you can derive that these are the equations of motion. Again, you can just do a sanity check, and let's say we set G string to 0. So that should be as good as forgetting about these string products, and what we get is the equation of motion, which we got in the first lecture, right? Which is just imposing the on-shellness. So then the statement is that the solutions phi star would be in one-to-one correspondence with consistent routes. So now, of course, just to do yet another sanity check, we have started with a consistent string background, right? So the trivial solution, so the trivial field configuration of phi star equals 0 should be a solution. And since these products are linear and they start with n equal 2, you can see that phi star equals 0 is indeed a solution. And that is connected with the fact that in this original action which we are varying, there was no tadpole, right? So that tadpole would have corresponded to an off-shell, a 1-point amplitude, which, I mean, if we reduce it to one shell, I mean, would have to give us an on-shell 1-point amplitude, but these things are known to vanish for a consistent string background, at least at a classical level. Of course, at a quantum level, the vacuum can get corrected, as I was trying to explain in the first lecture, and then phi star equals 0 is no longer a solution, and we have to do vacuum shifts. So then let's try and elucidate further with the statement that the classical field configuration phi star should correspond to other string backgrounds. So in particular, what we can do, we can take this field configuration phi star and expand in small fluctuations around it. So that in principle, if we substitute this expansion in small fluctuation into the original action, that should give us a new action for the fluctuation, which should give us the physics of this background, of this would-be background, which correspond to this classical solution. And if this is to be a consistent string background, that new action would better be a consistent SFT action, right? So let's see if we can get this. So the strategy now is to take the original string phi and expand it in small fluctuations around this classical field configuration phi star. Yeah. And substitute this expanded string field into the original action. So that defines a new action for this fluctuation order phi, which I will call order S. So by definition, this is capital S, capital phi star plus lowercase phi. So now let's see what we get, right? So first of all, what we get is just a constant, which is the on-shell value of the original action. Right? So let me actually make some comments about this on-shell value later. But now let me continue in the expansion procedure so as not to lose momentum. So first of all, what we get is something which would be a tadpole, right? So this tadpole, I can represent it again with a string product, this time a zero string product, which takes 0 inputs and gives you 1 output, right? But if you really expand this section, you can of course explicitly derive what this tadpole is, right? And that tadpole turns out to be nothing but the equation of motion for this capital phi star. So this is good, right? This is saying that if the configuration around which we're expanding, and I think it's something which is more or less obvious, if the configuration around which we're expanding is a classical solution, that corresponds to saying that the expanded action will have a vanishing tadpole. Okay. So then we can continue. And we can construct the kinetic term of the expanded action. So that will come with some expanded BRST charge, shifted BRST charge little q, where this little q can again be defined in terms of the action of this little q on the fluctuation phi can be defined in terms of the action of the original BRST charge capital Q and the classical solution, right? Again, after you do your algebra, the answer thing is the following. And then this is to be, the expanded action is to be consistent from Q theory. That new operator little q would better be nilpotent, right? So then, okay, again, in view of time, I give it to you as an exercise to show that as a consequence of these original string product capital and satisfying the infinity relations, and also as a consequence of this 5 star satisfying the equation of motion, we can show that this is indeed the case, that u squared is equal to 0. Oops, equations of motion. Okay, and then you can continue. You can, in a similar way, you can define all the higher interacting vertices, or compute actually the higher interacting vertices of this expanded action. I will not write down an explicit expression for these, okay, but the story is then precisely what you would have expected based on what you got for this view. Again, as a consequence of the infinity relation satisfied by these products capital L, and also as a consequence of the equations of motion for pi star, you can show that these products little l, they satisfy L infinity relations.
You start from the Wittens cubic one, and you go to some different background.
Yes.
Then can you make a field redefinition in these little phi's to bring it back to the Wittens cubic form? Or?
Actually, you don't even have to. I don't think you even have to. I have to make a. Okay, I will have to think about this if this property preserves associated with the of M2. Yeah, perhaps we can do this computation after the lecture. Sorry, I think that should be something which I should know and which should be obvious, but yeah, I'm just not sure at the moment. But certainly there should. I mean, if it turns out to be not to be associative, the shifted product, and we should be able to make a future definition to make it associated. Yeah.
What does associative have to do with my question?
Well, if I mean, Witten sphere being cubing
it's
is
the same thing.
equivalent to M2 being associated.
I see.
Okay.
So if it's associative, then there's a field redefinition which brings it back, which brings it to the.
Yeah, I'm certain there should be, right? But yeah, let's see. So this series of statements which I just made, I mean, should hopefully elucidate in what way the classical solution should be thought of as different consistent backgrounds. For string field. And then okay, equivalent to the statement is it also saying that it's action little s, which I was writing down as an expansion in terms of these small fluctuations should be thought of as the SSD or SA actually as a string field here around the new background after the definition. So then in order to find some properties of these backgrounds associated with the solution of phi star, and in order to either to match them to something which we know, or in order to identify properties of some new backgrounds which might be discovered in this way, we of course need to know how to compute observables, right, associated with this phi star, and using this new expanded action little s of little phi, I mean that can be done, right? We can, for instance, take this this new BRST operator with a Q and use it to compute the spectrum of on-shell physical string states around the new background by determining or by computing the cohomology. So Q is completely determined in terms of the original Q, in terms of the original string products, and in terms of the classical solution. So in principle, if we have infinite computing power, we can compute the cohomology and thereby determine the spectrum.
How do you know what the L0 is? The new L0? Or the weight? I guess you mean spectrum is a spectrum of scaling dimensions or masses or.
Yeah, I mean by spectrum I mean the set of physical states, and from the set of physical states I can then read off the masses, right? Actually, at this point, this is abstract. I will give you concrete computational methods in the next lecture, right? Because in the applications of specificity into the CFT, determining the spectrum, let's say for solutions corresponding to short RG flows, will correspond to determining the anomalous dimensions of the operators, right? So there is a concrete computational scheme how to extract these anomalous dimensions from the cohomology of the shifted BRST charge. Okay.
My point is that homology is just a vector space.
Yes.
It doesn't have more structure, but there's the L0,
yes,
which is
I know. So okay.
It's okay.
Can you wait for the next lecture?
Yeah, sure.
I mean, it's a very nice algebraic procedure,
Yeah.
which was originally implemented by Ashoksen, and but it is yeah. I think you will appreciate it when I give you the details. Okay, but there is a computational scheme of how not to extract just the vector space, but also the let's say the eigenvalues of the L naught around the new background. Okay. Yeah. So. But not only that. So given that you can determine the spectrum of or the set of physical states, you can then compute the on-shell amplitude. So that should give you yet another set of observables through the Feynman diagrams. The computers of the Feynman rules given by this action as a part. So then of course, I mean, in principle, if you can compute these quantities, I mean, that would be good. But in general, I mean, yeah, extracting the on-shell amplitudes, even for the unshifted background from string field here turns out to be hard, let alone for a shifted background. So you also need some simplest observables, which will be given by the simplest possible amplitudes which you can think of, and these would be the partition functions, where you don't have any external states inserted. So, so an example of such an amplitude would be precisely the on-shell value of the action. Right? So, so that is supposed to be related, that is thought to be related to a shift of the worksheet partition function when going between the two backgrounds described either by the trivial perturbative solution phi equals 0 and the classical solution, right? So if those two background for those two backgrounds we can compute a worksheet partition function, the shift in the partition function should be precisely measured by the on-shell value of the action. Now, this statement it's kind of still on a very experimental level of understanding in the case of the flow string. This on-shell value of the flow string action is supposed to be in some way related to the shift in the sphere partition function of the two backgrounds. While in the open string case, and this statement is very, very solid, and it has been shown to work on many examples, precisely because of the fact that in the open string field theory, since we have a simple formulation of the action, I mean we can devise enough examples to actually test this statement and prove this statement. Yeah. So in the case of OSFT, we have this very, very simple observable, which is just the on-shell value of the action, and which measures the shift in the disk partition function between the old and the new backgrounds, which at the level of the worksheet CFT can be translated after factor into shifts in what we call the G function of the boundary conformal field theory. Okay. So now, finally, I was about to give you an example of I would say the simplest class of solutions which we can construct in SFT, and these are the marginal deformations. But in view of time, I will probably not do that right now, and I will somehow try and subsume this example into the next lecture where we talk about the applications into DCFT. So with that, I would just stop here.
Great, thanks. Jets.
Is there a proof that the cubic closed string field theory does not exist, or?
Yeah, there is a paper by Barton Spivak in which he gives a no-go theorem. I can give you a reference later. I think it's from the early 90s. So from that period, we should be able to find it.
So what doesn't exist? I didn't.
There's a no-go theorem for cubic closed string.
Cube. Yeah.
But there are certain okay. This no-go theorem has some assumptions, right? And so by violating these assumptions, I mean you can perhaps also violate the no-go theorem, right? So for instance, if you start adding more and more fields into the game, some auxiliary fields, I mean. In particular, if you are able to add an infinite number of these, you should be able to build an example of a cubic closed string field theory. But that would kind of rob you of all the computational power, right? Because you would introduce an infinite number of action degrees of freedom. So I guess the question is whether there is an example of a cubic closed string field theory with just a finite number of auxiliary fields added into the game. That's that's actually one of the research directions which is kind of active in today's community.
Can you maybe summarize once again? If you were to explain to a mathematician what is string field theory, then okay, we have this either L infinite or infinite algebra, but before that we need to have some vector space. And what structure do you need on the vector space? Like, for example, do you need a split into BC part and non-BC part, or can you just forget about that?
Yeah, I think if you want to make some contact between what you construct on the algebraic side and between some physics of some strings propagating on some space-time, I guess you have to assume that the Hilbert space is as that particular structure, right? So otherwise, it is not clear that what you're computing is really what you. Otherwise, it is not clear that what you have is really over a cheat. Well, maybe what I've said is not entirely correct actually. So for instance, that split into the matter and we see those CFTs of course manifest at the level of the perturbative vacuum, I mean, which you use to construct this SFT, right? But then when you expand around the solution in small fluctuations, right? And even though you know that in many cases what you found should be yet another consistent worksheet CFT background, it is no longer manifest at the level of the expansion action. I mean, how that would be split in the CFT matter of the new background and the BC dot CFT, right? I mean, that action which you obtain here, I mean, that action expanded in small fluctuations, that is completely written in terms of the variables of the original worksheet CFT in terms of the original matter and original BC ghost, right? So although that split is there, that is no longer the split of the new background, right? Yeah, and yeah, so and then again, as I was trying to emphasize in the first lecture, I mean, some of the solutions may not even correspond to the consistent string backgrounds, which would be obtainable from a worksheet CFT, like
plus BC.
Yeah, plus BC, right? I mean, you can, yeah, you can hope to find a solution to go string field theory with an NS5 brane, right? And yeah, the degrees of freedom of NS5 brane may not be, strings in the conventional sense, right? Mm-hmm. Right. So perhaps requiring the split into matter and BC ghost CFT maybe too unnecessary.
Okay, so if we don't, but what do we need then if we don't need that? Yeah. Do we we need a ghost number or did we?
I guess we need some grading, right? Yeah, I mean that is an interesting question.
You just wanted to formulate some bootstrap problem, like to class, I guess.
Yes.
Classify whatever string theory. I don't know if it's classifying string theories, classifying string backgrounds. I don't know. Just of course, it's very ambitious.
And it's yeah, indeed, it is, but it is an important question to ask. Yeah. Yeah, I think that also goes into the direction of obtaining a formulation of string field theory which will be manifestly background independent, right? I mean, the background independence here at this level of the SFT, of the form of the SFT which I was showing you, I mean, it should be there, right? Because at least to a very large extent, I should be able to obtain a very large class of consistent string backgrounds, from any starting consistent string background by constructing classical solution, right? So to a large extent, I mean, the action which I wrote down should be background independent, right? But that background independence is certainly not manifest because it is expressed in terms of variables which heavily depend on the choice of the background which I'm starting with, right? So perhaps what Daimel is thinking about would be a good starting point of trying to formulate like manifested background independent action, something like Einstein-Hilbert action for gravity, right? That also doesn't depend on a particular classical solution around which you're expanding.
All right. And you let's thank Jakub again for the very nice session.